We thought we would mark this occasion by introducing a regular feature.
Everything is data. Therefore, storage is what I call an everything problem. And these everything problems are just hard.
Increasingly, we're seeing government involved in investing in new technologies like quantum, which have such promise.
In a field where the US really doesn't have a lot of entries.
From Orion X in association with Inside HPC, this is the At HPC podcast. Join Shaheen Khan and Doug Black as they discuss supercomputing technologies and the applications, markets, and policies that shape them. Thank you for being with us.
Hey everyone, I'm Doug Black. Welcome to At HPC podcast, and I'm with Shaheen Khan. Shaheen, great to be with you again.
Great to be with you. It's just the two of us today.
Yes, indeed. And I think we were reflecting that this is actually our 20th episode of the podcast, which feels a little bit like a milestone in the early stages of what we're doing.
It sure is. And we're actually counting our double edition Christmas episode as one. So,
along with the special episode we did about HPC and cyber warfare when the war in Ukraine broke out. So we thought we would mark this little occasion by introducing what we think will be a regular feature where we'll start off each episode with a quick review of the major news in HPC of the week. We just thought we'd call it Top of the News.
Top of the News sounds good to me.
News broke yesterday or late Thursday, actually. It's $25 million in federal funding for quantum R&D involving Global Foundries, the semiconductor manufacturer, which last year, I believe, announced it was moving its headquarters to upstate New York, and also PsiQuantum, the quantum development company.
I thought it was a good move because I think this is government's way of basically hit two birds with one stone, because it obviously helps the semiconductor business with Global Foundries, but also advances quantum computing in a field where the US really doesn't have a lot of entries, and that's photonics quantum computing. So PsiQuantum, a very solid team, are pursuing practical quantum computers based on photonics. There are other players. The most major one is China, because China has actually demonstrated photonic computers that are providing some kind of quantum advantage. The other players in that market are Xanadu, a company in Canada and Toronto, also a very solid team, and Orca, an offshoot of Oxford University, which are very advanced in optics and photonics, also an extremely solid team. And there are a few others in Europe. There's one in the Netherlands called Quix. There's one in France called Quindela. There's one in Wales called Tundra. And I'm sure maybe others. So it's an approach that is very interesting because it can operate at room temperature. Now, not everything will operate at room temperature, but it's a lot more room temperature than anything else. And as a result, it's really interesting. So I thought it's a good way for the government to advance photonics quantum computing. PsiQuantum is the only American option, really. There's a supply chain to photonics that even non-photonics quantum computers can take advantage of. But in terms of building an actual computer based on photonics, these are the players.
And the idea, of course, is to integrate this quantum photonics within a chip, which is where Global Foundries comes in. This also seems to kind of echo the whole indigenous technology notion that major geopolitical players obviously recognize the critical value of technology in their global competitive standing. So increasingly, we're seeing government involved in investing in new technologies like quantum, which have such promise.
Absolutely. I think all the governments remember the past 100 years, and every time they skipped the technology, they regretted it. So this time they, as I keep saying, everybody wants a seat at the table, and they're willing to pay for it, and they're willing to take their chances, because if it does pop, it's going to be interesting, and they want to have a play. Now, PsiQuantum, as you mentioned, is interesting because they're trying to combine silicon with photonics, and this is their way of getting to 1,000,000 qubits with pretty solid error correction. So it looks really promising, and it's a good thing to try to push.
Okay, then there was the AMD acquisition.
Right. So AMD announced that they're going to acquire Pensando, a company that's been around for a few years and had raised significant dollars, including from HPE. They are in the DPU business, the data processing unit. Several of those players call them. It's not a very thin market anymore. It's pretty crowded. Obviously, NVIDIA with Mellanox have their Bluefield DPU. Pensando has theirs. Fungible is another company that has DPUs, and it was also one of the early ones. AWS has a chip called Nitro that's been around for a good while, and they've been using it in their own systems. And Intel has their infrastructure processing unit, IPU, that has DPUs inside, or you could argue it's kind of a DPU thing. So this is all becoming a bit of a frenzy. And I think because networking can afford to have really long pipelines, and long pipelines can benefit from FPGAs, you could also argue that there is alignment with Xilinx, which is the acquisition that they're about to complete if they haven't already.
And then we have Fujitsu, which announced Fujitsu Computing as a Service, which offers, among other things, their quantum-inspired digital annealer technology, their AI and machine learning software, but also the technology used in the ARM-based Fugaku supercomputer, which has been ranked the world's most powerful HPC system, I think, for 18 months now.
Yeah, I think that's also a very good idea. The farther away you go from the major players, AWS, Azure, Google, IBM, Oracle, the more local players have a basis to build a business. So you see regional cloud providers, both in the US, but also in Europe and in Asia. So I think Fujitsu has an opportunity, not to mention the Chinese players. I see cloud providers increasingly focus on all the different configurations and hardware capabilities that they can offer as a differentiator. And for Fujitsu to offer their digital annealers, they've got an AI accelerator chip that they can use, and they've got now with Fugaku something that is world beating. That's all really interesting.
Exactly. So, and by the way, as an aside, ISE is coming up next month. We'll see if Fugaku is still number one. We assume it will be, I assume.
Yes. Well, the systems that these guys build with the K computer before this and now Fugaku, among other things, they're just beautiful machines. So just looking at it would be fun to do at ISC.
Yeah, I've heard you rave about the beauty of Fujitsu systems.
Yes.
So our main topic for this week is storage. This is something of a two-part discussion because next week's special guest will be a storage legend, Gary Grider, who's the leader of the HPC division at Los Alamos Lab. And he's really had a major impact on the development of so many key storage technologies over the last 35 years. And Shaheen, yesterday you and I were chatting about storage, and I recall a conversation I had with an IBM storage guy about 5 years ago. He was a real storage enthusiast, great guy to chat with. And
yes,
he said in his career, because he was an old IBM hand, I think he said he had met one CIO who had come up through storage as that person's core discipline. He also said, he has that sense that storage kind of lacks some sex appeal. I mean, what do you make of all that?
Well, I think historically that's been true. And well, also historically, servers have been the focal point and had the center stage.
Yeah.
And when we all got started, it was the big computer. You had some disk and tapes hanging off of it. In the early days, you didn't have networking at all. You just had terminals that were attached. But over time, you had networking that got created. But what happened over the past 10, 15 years is that what used to be a server connected to disk and connected to networking, that networking piece has become a universe of a networking stack, such as DPUs. And then what used to be an IO bus, and then I don't really care what's attached to the other end, has become this universe of storage with storage area networks and network attached storage and direct attached storage. And you have persistence and speed and security and virtualization and containers. And you're going from real data to synthetic data to simulated data. You go from private data to public data to acquired purchase data. You're going from structured to unstructured. You're going from files to objects. So it just like proliferates. And all of that, of course, adds a lot of complexity, and it provides market opportunity for all sorts of new players that crop up every year. But it also increases the value of data. So I think that as data becomes better recognized as an asset, and that leads to data scientists and data-centric AI and the data economy, I think you're going to see storage and data-centric folks become more and more prominent.
Yeah, and we recall a piece that came out in The Economist, I want to say 4 to 5 years ago, that said data is emerging as the world's most valuable commodity, most valuable asset. As the world really becomes digitized, that means all that data has to be organized in a way that's accessible So it can be analyzed, used however it is used.
Right on. And I think this is an area where the HPC community, once again, has led the way and has a lot to offer. And of course, as we will hear from Gary, there are few storage technologies out there that HPC hasn't touched. And many of them Gary personally hasn't touched. But that's because of scale, because HPC has been dealing with that for a long time. Data that has different attributes and qualities. For example, if you look at astronomical data, that data doesn't change. So cannot be tiered. It needs to be accessible at all times, and it is giant in size. So the different use cases of data for different kinds of applications also shows up across the board in HPC.
Constant innovation going on. We want to just quickly review some of the categories of storage where a lot of activity is happening. We've got NVRAM, for example, non-volatile random access memory. Explain to us why non-volatile in particular in an HPC context. Why is that such an important consideration?
Well, I think speed is probably the number one attribute for HPC and, of course, in general for others. And when you look at a storage memory hierarchy, at the top of it, you've got really fast memory registers and static RAMs and other things that are pretty close to the CPU. And all the way at the other end, you probably have like tape drives and everything in between. So you go from magnetic tapes to spinning disks. And then from the top, you come down to normal DRAM. So there's a class in the middle, the so-called storage class memory, which is fundamentally solid state. And of course, the consumer markets with flash drives has been driving a bunch of that. But there are other technologies too that play a role. And that means that there is a space in the middle where you can use technology and treat it like memory, or you can treat it like disk and provide a level of cost and speed and size that can fill that gap. So NVRAM does that in a really good way.
Yeah. And then there's this, I think, fascinating concept of computational storage, which is offloading some of the processing that needs to be done from the nodes out into the storage environment.
Right. I think this is what we called in situ computing, computing on the spot on where exactly you are, where the data happens to be, rather than moving the data. But it also fits, in my mind, to the whole serverization, as somebody called it and as we call it, where if you are looking at a storage and it needs to do things that are best done at storage, for example, dedupe, replication, encryption, compression, these are the things that storage controllers said, well, I can just do that myself instead of having the server do it. And it's better, faster, cheaper for all involved. So you start by doing that. And by doing so, you're offloading what the server used to do because the task is fundamentally a server task. And you can say, look, I got processing capabilities. I can do it myself. The networking guys do the same thing. They offload some of the network processing to the switch because there's CPU capability there that you might as well use for that. Even memory controllers can do some computation at memory, and that leads into processor and memory capabilities. So essentially, the question is, I've got now an expanse from edge to cloud and back, and there's data everywhere. Wouldn't it be nice if I just did all the computation where they happen to be? So to me, computational storage is an attempt to recognize that and do more and more at storage because you can, and you can offload somebody else.
Yeah. And then we have erasure coding, which was kind of a new concept to me. It's sort of, I guess, a more efficient approach to data protection relative to RAID, which is redundant array of independent or inexpensive disks. But talk a little bit about erasure coding, this sort of fragmentation of data without complete replication.
This is actually another example of using some kind of computational capability to have a faster algorithm for recovery. So obviously with RAID, you replicate data in some manner. Either you do file striping like we did in the early days, or you go to other more sophisticated or different ways of replication. So with erasure coding, you segment the file into pieces, but then you add additional data to those pieces that talk about what other segments have. So now every chunk of the data has some knowledge of what data resides in these other chunks. And if one of those chunks isn't available anymore, the others can bandy together and reconstruct the data that was lost. Now, that's just in a simple way. You can have it in a more sophisticated way. But fundamentally, it relies on the ability to reconstruct the data, and they call it forward error correction, by incorporating the data that you might need to do that recovery. And because you now have processing capability that is available and plentiful. That's faster than trying to go and grab it from a replicated piece, and it's also less storage.
Then we have this critical factor of metadata, which is really labeling or data about data that enables data scientists and data analysts to organize data that they're going to be using.
Metadata, you could say that has been around forever because you needed to describe where the file is and how many records and how many blocks and blah, blah, blah. But then over time, you can have additional data about data. You can describe the data in ways that allows you to do certain things faster or certain things that you couldn't do before without reading the whole file. And as data becomes more valuable and more complicated, that metadata becomes more important.
And more of it.
And more of it, exactly. It also has an impact on security and privacy because with sufficient metadata, you can actually glean some of the data that you are trying to protect. So in terms of personally identifiable information and things like that, that's an issue. So it's a very important part. And of course, you have to store metadata somewhere. So how you optimize that is all over the map. And there are solutions that optimize it this way or that way and therefore have a market traction. I mean, in general, everything is data. And therefore, storage is what I call an everything problem. And these everything problems are just hard because they're everywhere and the use cases are numerous, if not infinite. And optimizing for each one is an opportunity, and you may want to do that. And I think that's why we've got so many file systems and so many storage products. And we have AI now, which relies on data. So now you really have to manage it really well. And then you also have to worry about the quality of data, because this whole notion of data-centric AI is pointing out that the quality of data has a huge impact on the accuracy of the model and the speed of convergence, and just has a ripple effect across the whole AI scene. So it's better to focus on quality of data in a big way.
Yeah, an enormous growing and evolving problem.
Yeah, looking forward to discussing all of this with Gary, and I'm glad we're finally touching on storage. Yes.
Okay. Very good. Yep. Looking forward to next time. So thanks so much, Shaheen. Good to be with you.
That's it for this episode of the @HPC podcast. Every episode is featured on InsideHPC.com and posted on OrionX.net. Use the comment section or tweet us with any questions or to propose topics of discussion. If you like the show, rate and review it on Apple Podcasts or wherever you listen. The @HPC podcast is a production of OrionX in association with Inside HPC. Thank you for listening.